Hello and welcome to another digital design class. In the previous class, we spoke about different type of functions, even and odd functions, exclusive or exclusive NOR, or XOR and XNOR, and how we can solve them using the K-map or the Karnaugh map. And we solved it for a couple of the odd functions and their minterms. Today we're going to continue with that and with XOR and XNOR, and also with 4-variable XOR and XNOR and parity code and so on. So the logic diagram for a odd and even function is shown here. On the right, you can see the 3-input even function, and on the left, you see the 3-input odd function. And as you remember from the previous class, if you may remember, let me zoom this in a little bit. For the even and odd function, by the way, we finished the general logic gates like the NOR and NAND and different combination, and how we can produce other logic gates with the NOR and NAND. And for the even and odd functions, we had the exclusive OR and the exclusive NOR. And we showed that how exclusive OR works and how exclusive NOR works and the even and odd function. But what we explained in the previous one was with 2 inputs. We had only 2 inputs. And here, we're going to explain how we have it with 3 inputs. Like if we have an XOR which has 3 inputs, and an XNOR that has 3 inputs and 1 output, obviously. And the table for the 3-input, A XOR with B XOR with C, which was sigma is 1, 2, 4, 7. And if you replace A, B, C, according and draw the truth table to that, find the minterms, you would get to this exact table. Now, what if we have 4 inputs? What happens if we have 4 inputs? So for a 4-variable exclusive OR function, we will have to draw a 4-variable K-map. And on the left, again, you can see the odd function. And in this odd function, I think I lose. Yep, just give me 1 second. So in this odd function, M1, M2, M4, M7, M13, M8, M11, and M14 are ones. And you can see the ones that are between them are zeros. So all of these are zeros or don't cares. We don't care. And for the even function or XNOR, it's the opposite. It's 0, 3, 5, 6, 12, 15, 9, and 10. And the function itself, again, we can simplify it, and we can proof it the same way that we did for the previous one, by finding the ones and zeros and solving the K-map for it. Now, for a 4-input, we're going to have similar to this one, but instead of having 1 XOR gate, we're going to have 2 XOR gates in the input. Now, where do we use exclusive ORs and exclusive NORs? We use them sometimes for parity generation and checking. Parity code is a type of extra bit that we add to a system to be able to detect and correct codes sometimes. And the way that we find it is like this. Imagine we have 3 inputs, X, Y, and Z. And if we have an XOR, and we XOR X and Y, and we have a second XOR, number 1 and number 2, and we XOR X or Y, and again with Z this time, this creates our parity code or parity bit, or P. And then we can use this parity bit again to feed it back to a 4-bit XOR system. Now, this one is a 4-bit system, even parity system. Again, why is it even? And I'll explain why. Because in this system, if the number of ones is even, you're going to have a 0 in the output. And if it's 0, you're going to have, if we have even number of ones, you're going to have 1 in the output. And I'll explain how it's done. And then we have a parity check. And the parity check, as I mentioned, we combine the parity code with the inputs again. This time we have 2 XORs in the input with 4 inputs. And we have 1 XOR at the output, which creates the check bit, or what we call a parity check. So if C is equal to 1, 1-bit error or an odd number of data bit errors exists. If C is equal to 0, we have a correct or an even number of data bit errors. Now this gives us the table for parity generation and checking. Here we have 3 inputs, X, Y, and Z. So if we have even or no number of ones, the parity code would be 0. If I have odd number of ones, the parity would be 1. So I have 1, 1 here, so I would have 1. Again, I would have 1, 1 here, so I would have 1 in the parity. Here I have 2 ones, so a pair of them, even number, so parity would be 0. Again, here I have 1, 1, so an odd number of 1, the parity would be 1. Next, I have 2 ones. Because I have 2 ones, and it's an even number, the parity would be 0. Again, here I have 2 ones, the parity would be 0. And here I have 3 ones, which is an odd number, and the parity would be equal to 1. Now, if I combine all of them, or X or all of them together, so X or Y, Z, plus the parity, then I create the check parity code, or the parity error check. And again here, if X, Y, and Z and P are zeros, I would have 0 in the output. If X, Y, Z are zeros, but the parity is 1, then I would have a 1 because I have odd number of ones. And again, here I have 1, 1, so odd number of ones. And I would have, again, 2, so even number of ones, and so on. Now to practice this, let's actually solve a problem. Imagine we have these 2 circuits, and C is equal to X, XOR with Y, XOR with Z, XOR with P. And X is 1, Y is 0, Z is 1. I want you to find P and C. So X, Y, and Z are 1, 0, 1. I want you to find P, the parity, and I also want you to find C, which is the check error. Let me know when you're done so I could start. Okay, let's solve it, yes. So truth table for an XOR, if the inputs, I'm going to mention inputs at X and Y, and the output as output or Q. If it's 0, 0, then it's 0, 0, 1 is 1, 1, 0 is 1, and 1, 1 is 0. So if we have even number of ones, it's going to be 0. If we have odd number of ones, it's going to be 1. So here we have X is 1 and Y is 0. So the output of the XOR would be what? 1. And what about Z? It's 1. So P would be equal to what? 0. So P is 0. Now we have P equal to 0. Z is 1. X is 1 and Y is 0. So 1 and 0 again is 1, and 1 and 0 again is 1. And the output would be what? 0. So P is 0 and C is 0. So 1, 0, 1. If we go 1, 0, 1. Now, the correct answer here would be 0, okay? But if in this situation, our parity code changes, okay? So imagine this scenario. Imagine this scenario. Imagine that X, Y, Z is 1, 0, 0. This is the correct answer. The incorrect answer, X is 1, Y is 0, and Z is 0. So we have an error in Z, which becomes 0, okay? Now I want you to find P and C for the new inputs, X, Y, and Z. Okay. Yes. So if I change 0 to Z to 0, 1 and 0 is going to be what? P is going to be equal to what? 1. Now if I change this to 0 and this to 1, 1 and 0 is going to be equal to what? 0 and 1 is going to be equal to what? What is 1 and 1? 0. So P is 1, C is 0. Am I correct? Yes?
What would you do with the P and the C?
Okay. Yes, so now let's find another scenario, and I'll explain how we do that. If, for example, P is 0 here, C would become 1. Okay, so what we get is, if we don't get P equal to 1 and C equal to 0, so the initial P that we got was 0, okay? And we know that this is correct. But here we know that P is equal to 1. Therefore, we know that something is going to be wrong here. We shouldn't have an odd number of, we should have an even number of ones. Okay. Now, the full table looks like this, as I mentioned. And when we have the ones, for example, if we have 1, 1, 1, Y, Z, and P are 1, then the check would be 1. If I have 1, 0, 0, 0, 0, 1, so 1, 0, 0, 1, then I have the code is equal to 0, meaning but the ones that have a parity, which are 1s, you can see that these ones, these are creating most of the errors. So when initially we know that the parity code is 0 and suddenly becomes 1, we know that 1 bit is wrong at one point. And I'll give you more examples on the parity and the check as well. But for now, when you are given this table, the only thing that you need to know that is that P is equal to X, XOR with Y, XOR with Z, and C is equal to X, XOR with Y, XOR with Z, XOR with P. And if we have odd number of ones, we're going to have a 1 in the output. If we have an even number of ones, we're going to have 0 at the output. Now, hardware description language is the language that we use for programming and solving these Boolean functions. We use different softwares to be able to do that. We have HDL and VHDL or Verilog HDL as well. HDL describes the design of digital systems in the textual form. We have the hardware structure, the function, behavior, and the timing. And we're going to discuss VHDL and Verilog HDL. This graph shows the top-down design flow of a HDL system. We have the specification, the RTL design and simulation. We have the logic synthesis, the gate level simulation, the ASIC layout, and the FPGA implementation. FPGA and the implementation is, after this point, is for an upper level, graduate level class, which is advanced digital design system, which is part of it is computer architecture, the hardware part, and also Verilog and HDL and VLSI and so on. Now, for the module declaration, we have an example. And in this system, we have some example keywords such as module, and module, input, output, wire, and, or, and not. This is a simple example. We have 3 inputs, which are A, B, and C are our inputs. And we have 2 outputs, D and E are the outputs. We have 3 logic gates, G1, which is an AND gate, G2, which is a NOT gate, and G3, which is an OR gate. If I want to write the Boolean algebra for this, it's going to be A AND with B, and then OR with C NOT. This gives us what? D. And what is E equal to? E is equal to C naught. So we're going to have 2 Boolean expressions for these, D and C. So D is going to be AB plus C prime, and E is going to be equal to C prime, and this is the OR gate again. Now, let's see in an HDL description, how do we write it? This shows the HDL description for the example, and it's a combinational logic module modeled with primitives. And by the way, I'll explain what is a combinational and sequential logic gate in the next lecture. But for now, just remember that the combinational logic circuit doesn't have any feedback and doesn't have any memory. So the Verilog model, the module would be simple circuit A, B, C, D, E. We would define our outputs and inputs and the wires. So we have the output, which are D and E. We have the inputs, which are A, B, and C. So output, input, and the wire, which connects 2 different stages of gates, is W1. Then we would define our logic gates, and which are our other modules. We have the AND gate, which is G1, which the output is connected to W1. This is very important. and the inputs are A and B. And for the NOT gate, the output is CE, so we will first write the output, and then we will write its inputs, okay? And therefore, G2E is the output, and C is our input. So pretty easy and straightforward. And then we have our OR gate, which is G3. Again, D is the output, and W1 and E are the inputs. And then finally, we have AND module. So you can see it's pretty easy. First, we would define the outputs, the inputs, the wire connections between logic gates, and then we would define our gates, which are AND, OR, XOR, NOT, whatever that is. And for the gate display, we have to show the timescale directives. What does this mean? So this is for modeling a real-world scenario of a digital logic combinational gate. And in real world, we don't have an ideal logic gate. We don't have instantaneous changes in the output. We have a delay, meaning because we have a system that is cascaded in series, if we want to find the output of G3, which is D, we first need to wait until we find the output of G1, okay? So first we need to get the output of G1, and then we can do G3. And this may take 10 nanoseconds, for example. So before 10 nanoseconds, I don't have any outputs. And 10 nanoseconds and 10 nanoseconds for the second one. So it takes 20 nanoseconds till I get the answer D. Doesn't make sense. And for E, if this takes 10 nanoseconds, I'm going to get this in 10 nanoseconds. So D takes 10 nanoseconds and E takes 10 nanoseconds and D takes 20 nanoseconds, okay? And this shows the output of gates after delay. We have the initial change, the time units. Again, input ABC 0001111. When we change them, it takes 10 nanoseconds, for example, for E to change. And then for D to change, it would take 20 nanoseconds, for example. So each stage takes us a little bit of time to adopt and to change. So this example shows the gate level description with propagation delays for circuits shown in figure 1, meaning we would actually show how much delay each gate has as well. For example, an OR gate takes more time. It's slower than a NOT gate. An AND gate is slower than an OR gate. So if I want to write the delays, NOT gate is usually the fastest. Let me show it in T, the time that it takes in nanoseconds. And then we have the OR gate, and then we have the AND gate. So if the AND gate takes 30 nanoseconds, the OR gate would take 20 nanoseconds, and the NOT gate can take 10 nanoseconds. So I'm going to actually adjust this up according to the table that we have. So this is 30 nanoseconds, and the OR gate takes 20 nanoseconds, and this NAND gate, NOT gate, would take 10 nanoseconds. So what happens at 10 nanosecond? At 10 nanosecond, I would only get E. At 20 nanosecond, I would only get the output of G1, or I'm going to call it W1. And at 30 nanoseconds, I can get, 30 plus 20 gives us 50 nanoseconds. I get D, okay? So 10 nanoseconds, 30 nanoseconds here, and 50 nanoseconds for the whole thing. And I think the table also shows us, yes, in 20 nanoseconds, you can see the whole thing changing. So at 10 nanoseconds, only E is changing. And for W1 to change, it takes 30 nanoseconds. And for D to change, it takes an additional 20 nanoseconds. So here is at 50 nanoseconds, we have 30 nanoseconds, and here we have 10. Is it clear? Okay. And this is just for example. In real world, this may be very different. We have some gates that the OR gate and AND gate are pretty close, like 10 and 11 nanoseconds. This is just for you to know how much it takes. And it highly depends on the type of gate that you are using. If you're using a TTL circuit or any type of circuits, and you can find these in the data sheet. So when you want to program this, for example, the 70 series is different from the 40 series, 400 series, and they're going to have a different response time. So here again, what we do initially is exactly the same. We would determine the output, the input, and the wire connecting them. And then we would determine the gates. So for the AND gate, we will put a hashtag sign, and 30 means it takes 30 nanoseconds to propagate the delay, or the delay that takes this gate to spit out the results. And the gate is called G1, and the output is W1, and the inputs are A and B. For the NOT gate, it takes 10 nanoseconds. It's G2, input is C, and output is E. For the OR gate, it takes 20 nanoseconds. It's G3, the output is D, and the inputs are W1 and U1. So this shows the test bench for simulating the circuit with delays. Again, we will show the wire DE and the registers ABC. And again, this shows an example, and the reason that I put this example is to show this simulation output. So you can see here that A, B, and C are changing, and D and E are not changing at all. And the change come after a certain point, which this depends on the delay that we have. Again, when you are solving this with a simulator, like an HDL simulating tool or something, if you don't see any results initially because it has a delay propagation delay, you just have to scroll, and I would show you, in most cases, you just have to go forward and see where the signal has reached its steady state and the final output.
Where are those bars on the bars at the beginning?
Oh, these are the propagation, the delays that you have from the AND gate and the OR gate and the NOT gate and so on. And some of them, and by the way, this is very important as well. When you are programming the codes, the gates, if you have a sequential logic gate, sometimes the input is already 1 or 0. So if you want to change 1 to 1, it's like immediate, They have a memory, therefore they have an initial value. And sometimes if you have like multi levels of combinational logic gates, until it reaches the end, the input is changed again. So you're going to have, continuous changing in this signal. And I'll explain more about this. This is just an overview of how HDL works. In the combinational logic gate and sequential logic gate, I would dive deep into the timing. And that's a very important concept. You're going to have a question on timing on your FE exam as well, and at least 3 or 4 questions in your final exam. The reason I don't want to get into timing is going to get very confusing at this point. This is just for you to learn the coding, and we have a propagation delay, so on. So this is an example of a Boolean expression for the circuit 337. We would assign D is equal to A and B, and we have that or with C naught. So this actually is equal to this AB or with C naught. And this was, for example, 337 from the book. And another example that we want to solve, imagine E is equal to A plus B prime D, and F is equal to B prime C plus B C prime D prime. So again, we want to solve for E equal to A plus B C plus B prime D. And F is equal to B prime C plus B C prime D prime. So we can simplify it using HDL. The outputs, again, here are E and F. Let me copy this so you can here. Why did I do that? So my outputs are E and F, so E and F, and the inputs are A, B, C, and D. And we can write it like this, HTO, we want to assign E is equal to A or with BC. This is or, the or sign, and this is the and sign. Again, the or sign, the not sign, or the bar, the or, and so on. So we can also, this is another way to write it, to simplify it. So instead of having each of them and the wires and everything, you can write it this way as well. So this is another way that we can use Boolean expression to just write it down. So user-defined primitives, the general rules is that it is declared with the keywords primitive, followed by a name and port list. There can be only one output, and it must be listed first in the port list and declared with the keyword output. There can be any number of inputs. The order in which they are listed in the input declaration must conform to the order in which they are given values in the table that follows. The truth table is enclosed with the keywords table and end table. The values of the inputs are listed in order, ending with a colon. The output is always the last entry in a row and is followed by a semicolon. The declaration of a UPD, or user-defined primitive, ends with the keyword end primitive. So here is an example of a UPD primitive, and we have the inputs and we have the truth table. And for the truth table A, B, and C, we can show the outputs D. So we learned that there are multiple ways that we can show and write an HDL code, just to summarize. And I'm going to get back to this. The first way to do it is by using logic gates and showing the outputs, inputs, and the wires and the gates. And obviously, we have to show the propagation delay. Next method is to use the Boolean algebra. And the Boolean algebra, in my opinion, is the easiest. You just assign E and F, or the outputs, and just write down the Boolean algebra. Or the third way, which is more cumbersome, and I would recommend avoiding this, is by using the truth table. For the truth table, you have to write down all the tables. And this is easy if you have 2 inputs or 3 inputs. When you have 4, 5, 10 inputs, this is going to be a lot of work. It's going to be difficult to do it. But the HTO system, the simulation, is capable of solving any type of logic expression if you use Boolean function, if you give it a logic gates, or if you even give it truth table, it could solve all 3. But the way that you have to write the code for it, it's going to be obviously different. The Boolean expression is the easiest. The logic gates sometimes get confusing because you have to follow the propagation and the delay if you have the delay. And the truth table takes the most time, usually. Sometimes the truth table, you can actually give it an Excel file as well. So put in all the inputs, outputs, and you can import it directly to this as well. So we're going to write it like this. Again, we can use the user-defined primitive as well. And this is an example. We have outputs as E and F, and the inputs are A, B, C, D. And the user-defined primitive 0, 2, 4, 6, 7, for example, A, B, C. And we have F, E, and D, which F is our output again, and E and D are the inputs. And where did we get E? It's the output of the first one. So we have a system, the UPD that we have. It has 3 inputs, A, B, C. And this input output is called E, and it's AND with another input D, and the output is going to be called F. And you can see here this schematic for circuit with a UDP. So these user-defined primitives, it's like a gate or a black box that has been determined before. You can imagine you put a 3-input XOR gate in here. We already know what the inputs are, the outputs are. It's like you have an IC that you know for which inputs gives you what output. And it's already in the library of the HDL. So what you can do, you can build a huge circuit, for example, and save it as a UDP, and then simply use this block to give it an output to another AND gate. Okay, so this concludes the gate level minimization chapter. And for the next chapter, let me see if we want to get to combinational circuits. So whatever we learned so far, we usually had 1, 2 stages of logic gates, and all of them were combinational logic circuits, or what we call combinational circuits. So what is a combinational circuit? A combinational circuit is a circuit that has no feedback, it has no memory, meaning the output, it depends on the input at that time. And as soon as you lose power, you're going to have 0 in the output, or nothing in the output, actually nothing in the output. And since the output depends on the input at that time, the previous outputs or the previous inputs have no effect on it. Therefore, when the input changes with a small delay, propagation delay, depends on how many levels of gates we have inside, the output will change as well. Obviously, for example, if you have a buffer still is a combinational logic gate, but when you change the input, the output would not change. Okay, but still it's considered a combinational logic gate. In this chapter, we're going to do the analysis and design. The analysis is that we are given a circuit and we find out its function. And the function may be expressed as a Boolean function or the truth table. Or we would design a combinational logic circuit. So for designing, we are given a desired function and we determine its circuit. Again, the function may be expressed as a Boolean function or a truth table. So 2 things. We may be given a circuit and ask for the function, or we give you a function and ask for the circuit. Okay. And very easy example for the design. And we already did this, like A plus B times C. So we have A plus B and all of that C. This is a very easy one. By the way, obviously it's not going to be that simple. So A, B, and C, and this is an AND gate, and this is the OR gate. So at the end, we have A plus B times C. So this is from going, for example, from a function to the design. Now for the analysis procedure, we first want to do the Boolean expression approach. This is an example that we have. It's better to. Now, for this example, can you tell me the first gate on the upper left? What is the output of that? Let me show it with the laser. Here. So here, the output of the first gate is going to be A, B, C. What about the second one? Here. Thank you. It's going to be A plus B plus C. Now, what about the third one? AB. The fourth one, and BC. And when you add all of them, it's going to be AB plus AC plus BC. And this is connected to what? F2. Now let's go back to solve those two. So T2 is ABC, T1 is A plus B plus C. Am I correct? Now what is the output of this AND gate here?
AB plus AC plus BC not.
Perfect. AB plus AC plus BC, all of that going through the NOT. And with what? A plus B plus C. And if I simplify, so if I have F2 prime over there, and here we use the De Morgan's law, F2 prime, the ANDs become OR, and we invert the variables. So therefore, T3, when we multiply it by that, this is just simplified. It's going to be A, B prime, C prime plus A prime, B, C prime plus A prime, B prime, C. And it's going to be the same as the previous one. If we just multiply R's, we're going to get the same result. And then this, what about F1? What would F1 be? F1 would be T2 plus this, so ABC plus all of that. And what happens if I add ABC to A prime, B prime, C prime? Yes. So if I add those, it's going to be 1. And if I add, and then I would be left with A, B prime, C prime plus A prime, B, C prime plus 1. And anything plus 1 is going to be equal to 1. Now, if I write the truth table for this, I need your help here. Now, this is the truth table approach to analyze this digital logic circuit. Now, if A, B, and C are 0, 0, 0, what would F1 be? Let me solve the, yes. So A, B, C are 0, 0, 0, this would be 0, yes? What about the second one? 0. So A, B, this is going to be 0. AC is 0, and this is 0. 0 plus 0, 0. This NOT would be 1. Now 0 on the top, and 0, 1 would be 0. So 0 plus 0 gives us what? 0. What about F2? 0. So F1 would be 0. And F2 would also be 0. Now, let's solve it for A, B, 0, 0, and C equal to 1. What would F1 be and what would F2 be?
Two is 1. All right, now F2 is 0.
What is the answer to the first gate? 0. Second gate, 1, 0, 0, 0. Am I correct? So this is going to be 0. So F2 is 0. If this is 0, this is going to be 1. 1 and 1 is going to be 1. Am I correct? So F1 would be what? So 1 and 0. So F1 is going to be 1, F2 is going to be 0. What if ABC is 0, 1, 0? What is the first gate? The AND is going to be 0. Second gate, the OR, 1. The next AND is going to be what? 0, 0. 0, 1. 1 and 1, 1, 1. What about F2? So F1 is 1 and F2 is 0. Now the first student to get the next one right gets extra point on their next assignment. 0, 1, 1. F2 is 1, okay. Perfect. Remind me to give you an extra point. So F1 is 0 and F2 is 1. Okay, perfect. So student to solve the next one gets the extra point on their next assignment. What if A is 1, B and C are 0, 0? The 1, 0, 0. What about F1? Perfect. F2? Perfect. Remind me to give you extra point. Just looking at it, you can. F1 is 1, F2 is 0. What about the next one? 1, 0, 1. F1 is 0. Yes. Okay. So F1 is 1, F2 is 1, and F1 is 0. Next one, 1, 1, 0.
Is a 1.
Perfect.
F1 is
Yeah, are you sure?
a
0. F1 is 0 and F2 is 1. And the last one, if all of them are 1, what happens?
one.
Mm-hmm.
F1 is a 1.
Yes, 1, 1. F1 is 1 and F2 is also 1. Now, we can use this truth table to find the Boolean function. And the way that we do that is by using the K-map or the Karnaugh map for it. Now, how can we do that? We can simply find the minterms and find where our minterms are 1 and replace it in the K-map. Since we have the K-maps that we have, we can also, the number of variables that we have, we can find the output there as well. Now, how did we get to this K-map? We have 2 in the power of 3, because we have 3 variables, A, B, C, 8 minterms. And again, the minterms are M0, 1, 3, 2. Let me write it down. M0, M1, 3, 2, 4, 5, 7, and 6. Okay. And this is going to be M0, 1, 2, 3, 4, 5, 6, and 7. Okay. So if I want to find the function f1, f1 is 1 at 1. It's 1 at M2. It's 1 at M4. and it's 1 at M7. Again, 1, 2, 4, and 7. For this particular case, we can't simplify it any further because they're very much apart. And you can see that we can use this and the K-map to be able to simplify this function. So for F2, for example, if I want to write the K-map for F2, can you help me for F2? We have to find where F2 is 1. So F2 is 1 at M3. It's also 1 at M5 and M6. Okay? And if I draw the K-map, I have M0, 1, 3, 2, 4, 5, 7, and 6. And by the way, this is B, C, and A. Let me use a different color. I'll use a black. So it's 1 at 3, 5, and 6. Again, since these are very scattered, I can't combine them. So we're going to have 3. Therefore, F2, if I want to use the Boolean function, it's going to be x prime yz, which is M3, plus x y prime z plus x y z prime. This is M3, M5, and M6. And I'll give you an example on that we can simplify actually these gates using Boolean algebra and the K-map. Now, let's go to F2. Oh, I forgot one of them, actually. M7 was also 1. Yeah, because it was on red, I didn't. So F2, actually, let's go back. If I want to write it, did a small mistake. So 1, 2, 3, 0, 1, 3, 2, 4, 5, 7, 6. This, and I forgot the last one. So M3 is 1, M5 is 1, M7 is 1, and M6 is 1. And I can combine these two, and these two. Combining these two gives us BC. Combining these two gives us AC. And combining these two gives us AB. So F2 would be equal to AB plus BC plus AC. I forgot one of them. So you can see that instead of having, and I'll show you how we can do that. Instead of having all of this, we can get one level further if we had more. If we had another one, for example, at M4, we could further, simplify it and make it much more easier. And if you look at these, it's going to be the exact combination that we have in the logic gates. It's going to be AB, AC, BC, all of them or together.
You were to group 5, 7, and 6 together. What would that look like?
5, 7, and 6. So that's a great question. 5, 7, and 6. Let me write it down. So when you want to put these pairs together, first of all, you can only do 2 or 4 together. So if I had 5, 6, 7, I can't put all 3 together. The only way that I can do it is going to be to pair them 2 by 2. So I can do 5 and 7 and 6 and 7. Okay. That's the only way that I could do. So 5 and 7, if I combine them, it's going to be equal to AC, and 7 and 6 is going to be AB. So to design a procedure, given a problem statement, we would determine the number of inputs and the outputs first. We would derive the truth table from that. We would simplify the Boolean expression for each output. We would produce the required circuit. So for example, we want to design a circuit to convert BCD code to excess of 3 code. BCD code is a 4-bit code, and it's between 0000 and 9, which is 1001. Okay. And the excess of 3 code is 4-bit, and the value is the value plus 3. So if you have 1, it's going to be 4, and so on. So how can I design a circuit to convert BCD to excess of 3? For that, first, we need to have the truth table. So the truth table for BCD to excess of 3, it's going to be a 4-bit code. And you can see that BCD starts from 0. The excess of 3 starts from 3. So you can see it's 0011, which is equal to what? Yes, so 0011, which is equal to 3. So anything that we have, the excess of 3 is going to be plus 3. And so on. If BC go to 0001, which is 1, excess of 3 would be 4, until the last one, which is 1001, which is 9 in BCD code, and for excess of 3, it's going to be equal to 12. Now, first, what we want to do is we want to create a K-map, and that K-map would have 4 variables. Obviously, because BCD code doesn't have any number after 9, number 10 to 15 would be our don't care. Okay. Now, the first K-map that we build is just for W. I'm going to build it from the right one. For the right one is going to be our input, and the output would be just for W. So imagine if W, X, Y, Z is our F1, F2, F3, and F4. And this one is just for building W. Now, where is W1? I have W1 here, here, and the rest is X, okay? So 0, 1, 2, 3, 4. This is 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Let me write all of them. Okay. And if I do the, sorry, the K-map, this is 0, 1, 3, 2, 4, 5, 7, 6, 8, 9, 11, 10, 12, 13, 15, and 14. So from 10 to 15, we have don't cares. 8 and 9 are 1, so this is 8 and 9. And also 5, 6, 7. So 5, 6, 7 are also 1s. This is how I just wanted to draw it so you can see how we got this table. Now we have to simplify it. So to simplify it, I can use the don't care and combine the 8 squares at the bottom. And if I compare them, if I combine them, I would have A, which is the purple one. And then the 4 on top of that in the middle, I'm going to have BD for that, the blue one. And for the green one, I'm going to have BC on the 4 on the right. Now I've created this for W. I want you to create it for X. So I want you to create a K-map for X. So the output is X. This is C, B, D, and A. And I want you to find X. What is X? Again, this is 0, 1, 3, 2, 4, 5, 7, 6, 8, 9, 11, 10, 12, 13, 15, and 14. I'll give you a few minutes to solve this K-map. I want everyone to solve this K-map. So first find where X is 1 in the second column on the right. And where it's, I don't care, they don't care what. Yes, yeah, yeah. I haven't solved it myself, but we will solve it. Yes, I think it's correct. Okay. So let's start from the top of the table. What is M0? This is 0. What about M1? 1. M2? 1. M3? 1. What about M4? Still, this is M4. It's 1. What about M5? 0. M7? M6? So M6, 7. M8? 0. What about M9? 1. And the rest of it is don't care. This is the table that we have. Now, if we want to combine them, use a different color. Can combine these two, and I can combine to make it easier. I can actually combine these four. And I can combine, let me use a different ink color. There are different ways to solve it, but I can combine these four as well. And I can combine these two. Another way to just combine the three ones on the top, and then the lower one, we can combine those four in the bottom. Both of them, you're going to have the same answer. So if I combine the four middle ones, I'm going to have B prime oh, by the way, this is A. Why did I? It's going to be B prime D plus the four on the right side, which I put together with the red. That is going to be equal to B prime C. And these two are going to be equal to B C prime D prime. So B prime D plus B prime C plus B C prime D prime. Let's see if we got it. Okay, it doesn't work. For some reason, the pen stopped working. So we can combine the two in the middle, the two on the right, to a left, and therefore X is going to be equal to B prime C plus B prime D plus B C prime D prime. B C prime D prime. Now for the next one, we want to find Y. And this is the truth table for Y. I want you to find the function for Y. What is the function for Y? What is Y? I'll give you again a few minutes to think on this. This is a relatively easy one compared to the previous one. Perfect. Yes, that's correct. Okay, so we can combine these four and these four. Combine these four, I'm going to have CD. And for these four, I'm going to have C prime D prime. So Y would be equal to CD plus C prime D prime. Now I want you to solve the last one for Z. Again, I'll give you a few minutes. And the first student to solve this gets extra points on their on their next assignment. So Z is one at M0, 2, 4, 6, 8. And the rest is don't care. Did anyone solve it besides you? What is the answer? Perfect, yes. Now, if we write the table, it's going to look like this. Simply, we can combine these four with the four. Or let me write it like this. I can do this actually. Combine these 8. If I do that, Z would be equal to D prime. Okay. Perfect. Okay, that's it for today's class. In the next class, we will continue with combinational logic gates. If you have any questions in the meantime, just please send me an email. Thank you so much and have a great day.